Good evening and a warm welcome to the JSPL webinar series on decoding of steel in high rises and mid rises. Let me just introduce you to the speakers of the day. First is our keynote address, Mr. V.R. Sharma, Managing Director, Jindal Steel and Power Limited. Vijay Ratan Sharma is a leading technocrat with more than 37 years of experience in steel, power, cement and mining industry. At present, he's working as a managing director of Jindal Steel and Power Limited, one of the leading conglomerates with interest in steel, power, mining infrastructure. He joined JSPL in June 2019. During his tenure, JSPL has undertaken several steps to transform itself, as shown excellent performance in all fronts. This includes an impressive higher production and sales and turnover during the COVID-19 induced economically challenged period. Under his leadership, JSPL recorded its highest ever consolidated figure in financial year 21. Let me now introduce you to the other speakers of the day. Huang Yu, Director, Web Structures. Huang Yu is a registered professional engineer in Singapore and currently works as a director in Web Structures. He has obtained an honors in Bachelor of Engineering degree in Civil and Structural Engineering from the Nanjing Architectural Engineering Institute and a Master of Science degree in International Construction Management, both from Nanyang Technological University in Singapore. During his 20 years with Web Structures, Huang Yu has worked with numerous world-class architects and structural sensitive projects in Singapore, such as the new MediaCorp building and in the region and beyond. Giovanna M. Vigano, Associate Web Structure, has joined Web Structures upon completion of his Masters in Civil Engineering from Polytechnic of Milan. He is one of the new generation of leading Websters and nominated associate to Web Structures. He is currently involved in web projects in Singapore and Malaysia, working on highly demanding schemes with world-renowned architects. Up next is Jay Shah, Director, Access Architect. Jay holds a Bachelor of Architecture at KRVIA Mumbai and Masters in Advanced Architectural Design from Columbia University, New York. After working in New York, Jay chose to return to his hometown, Mumbai, to join Access Architects, and currently he heads the organization as a director. Mr. Shah, at the age of 30, is already well recognized for his leadership in sustainability and usage of new technology and being able to appropriate it for the specific needs of each project and client. Subrat Panda, VP and Business Head, Structurals, Jindal Steel and Power Limited. Mr. Panda is currently working as Business Unit Head, JSPL, and has been working for over 28 years for the steel industry. He is an electrical engineer, started his career with SAIL when he worked with Central Marketing Organization. He was a branch manager when he decided to move to JSPL after working for about 20 years. He's an avid reader and a fitness freak. Dr. Anil Agarwal, Assistant Professor, IIT Hyderabad. Dr. Agarwal earned his doctorate in Civil Engineering from Purdue University, USA, and a bachelor's and master's degree from IIT Kanpur. He's an Assistant Professor in the Department of Civil Engineering and IIT Hyderabad. His research interest includes behavior and design of structures under fire conditions and other extreme events such as blast and earthquake. He has more than 10 years of experience of investigating and analyzing the behavior of structural system under extreme loading condition. Before I hand over the session to Mr. V.R. Sharma, requesting all the attendees to please participate in the poll and do post your question in the question Q&A chat box, which will be taken at the end of the session. Over to you, sir. Thank you.
Yeah, thank you so much. Good afternoon, ladies and gentlemen. This is a wonderful platform to speak with all of you. And the subject is how to enhance and how to increase the capacity, how to increase the consumption of high-rise buildings, and how to increase steel component in these high-rise and mid-rise buildings. So this is a very interesting topic. I think everybody will be enjoying. We have many of the researchers, we have the people from the design institutes, we have the people from the user industry, and I'm sure everybody will enjoy today's webinar. The steel industry had been passing through a very, very difficult time in last 1.5 years during the pandemic one wave, that is from February 2020 and then again pandemic 2, that is wave 2, that is in April and May 2021 in India. I mean, that has thrown a lot of many challenges in front of the people as to how to work together and how to find the solutions in the interest of humanity and the mankind. So steel basically is a major component today in the growth of any economy, and building construction industry is definitely plays a very, very vital role. So today we are seeing that in India the trend is picking up. Most of the commercial institutes, most of the malls, most of the office buildings are coming made out of steel. Earlier, these were all through RCC structure, and they have their own limitations. Sometimes there are always questions that when we construct a building through RCC, we can reach to in $20 or maybe $25 per square feet, whereas through steel structure, we have about 10 to 15% higher cost. But often we forget that steel, by its nature, is a product which can be recycled in future, whereas the RCC cannot be. So that has to be demolished fully. The other area is we take at least 35 to 40% less time in constructing a building than the RCC structure. So the point here is the entire country today is working as to how to build more and more steel-based building, steel framing building, structural steel building than brick and mortar or than the RCC buildings. The another major reason today is because manpower is in short supply. Due to pandemic, most of the sites were closed. People, they have migrated to their hometowns or home states, and there's a acute shortage of labor, acute shortage of skilled people at different sites. So most of the projects in major towns in India, be it NCR, be it near Bombay or Pune or Bangalore, Hyderabad or Chennai, most of the projects are in standstill condition, or they are just crippling with a very, very low speed. So this is, a very major factor today, which has allowed or which has forced the designer, the architects to understand the importance of steel. Today, we are seeing that not only in the high-rise buildings, but even for the light gauge structure is being used for the single-story and double-story buildings. The earthquake resistance, the fire resistance, and the shortage of manpower, such kind of requirements are attracting the steel buildings or the solutions through steel. So most of the now the structural engineers and the design engineers, including architects, they are working as to how to increase the usage of steel through the steel structures building in the country. I'm sure the future is bright. The industrialization is going to take place in a big way. Steel industry is going to grow at the rate of 10% YOY. Finally, we have to reach in India a target of 300 million ton as declared by Government of India and Niti Aayog. So 300 million ton by 2030 means more and more steel will be available tomorrow, and the steel will be available at a very affordable price. Today, the country's capacity is 135 million ton, but we produce only 110 million ton maximum. Last pandemic year, we could do only 102 million ton. So today we are not utilizing our full capacity, but if we grow at a 10% to 12% YOY, then definitely we'll be short of steel by 2025. Government of India is working very hard with the industry for the brownfield and greenfield expansions. I'm sure that by 2030 we can reach to a target of 300 million ton. So today, as I told you, the installed capacity is 135 million ton, whereas the delta from today to 2030 is 165 million ton. So this means at least 10 more plants can be absorbed in the country, having 15 million ton or 16 million ton of capacity, or maybe 30 plants of 5 to 6 million tons of capacity. So this shows that more and more steel will be used in constructing the plants also, because the entire structural steel is also used for the steel industry. So when the steel industry is flourishing, the steel industry is using the steel structure, then the MSMEs and the downstream industry, it is their turn. Because when you produce 300 million ton steel, that means this will be multiplied in different kind of usages by 5 times or 6 times. That means the value addition will take it to 300 million to 1,500 million ton. So this means the steel components, steel buildings, steel items will keep on changing the hand from one application to another application. So some people will be doing some intermediate job, some people will be doing this service center job, some people will be doing fabrication welding job, some people will be doing erection job, and some people will be giving a final shape to construct a world-class, very modern building, and which can also reduce the CO2 emission in the country while making the steel. Because most of the steel, when it will be recycled, this will go to electric arc furnaces, and finally, in times to come, when the recycling takes place, this will be a very, very low CO2 creator in the world. So coming back on steel industry as a whole, there are many players in the country, those who produce steel structure. We at JSPL, we are one of the largest steel structure producer. So we have rolled beam, rolled sections, rolled angle, channels, and other specialty products like sheet piles. We also produce rails. We also produce the welded structure out of plates. We are the largest plate manufacturer in the country, and we provide solutions, plate welded structure or the rolled structure. We prefer to give a solution through the rolled structure because that is cheaper in terms of total cost. Today, if you see the plate welded structure, it costs about 1 lakh rupees per ton, that is 100,000 rupees per ton. And or in whereas it is, if it is a rolled structure, that is costing about 55 to 60,000 rupees a ton. That means about $700 to $800 a ton. So the difference is about $300, and which is a huge difference. And the cost of constructing a building through the rolled structure is less than the welded structure. So that is also an added advantage of such kind of products. We are also working as to how to galvanize the structure in times to come. There are already some players, those who are galvanizing the steel structure, and we are also adding some more facilities so that galvanized structure can be given for the building construction in time to come, even for the multi-story and high-rise buildings. Similarly, the another major consumption which is likely to be that Government of India is looking to go for the high voltage transmission lines from 230 kV to maybe 750 kV and finally to 1200 kV. This is where we use heavy structures, heavy angle irons, even up to level of 250 by 250 and 35 to 40 millimeter thick. All these angle irons are galvanized and finally find a place to construct the transmission towers. So that is another big area. Government of India is doing electrification, and Government of India is adding more than 10,000 kilometers of railway lines and the electrification together so that the country can be free from diesel locomotives or any other kind of locomotives. Only the electrical locomotives will be used in the country, and that means more and more electrification will take place, and that immediately increases the consumption of steel, and especially the galvanized steel for the transmission of electricity for Indian Railway. The Indian Railway is now working how to consume more than 1.7 to 1.8 million ton of rails in the country. They had a plan to reach to 1.7 million ton last year, but unfortunately because of COVID, they couldn't do it. But I'm sure by 2023, they'll be consuming about 1.8 million ton of rails. That means in a corresponding value, it will be more than 1.5 million ton. The steel structures will be used. So there is a good potential today in the country. And if we grow on YOY basis, year-on-year basis at the rate of 10%, then the growth will be phenomenal. So this is where we are today, that we want to reach to that level. And we want to promote and encourage all of the researchers, scientists, all of the engineering colleges, all of the structural engineers to please work on the high-rise buildings, steel structure buildings, so that we can create a better world for tomorrow. Thank you very much. Hello.
Thank you so much, sir.
Yeah.
So you can, when you, sir, you can start the presentation.
Okay, I'll be sharing my screen. Can you let me know if you can see the screen?
Yes, sir, we can see the screen.
Okay, fantastic. All right. Good evening, everybody. This is Giovanni from Web Structures, and we're very happy to be here to talk about steel structure and to give you all an international perspective on steel structure, steel engineering. We'll start with a small introduction about who we are, and then we will fly you through some structure in Taiwan and Bangladesh, and end up with some selected project in other countries worldwide. So Web Structure is a civil and structural engineering consultancy firm headquartered in Singapore with offices in Kuala Lumpur, in the UK, as well as in China. But recently, as recent as 1 year ago, we joined forces with Rambo, which is an international company, multidisciplinary, headquartered in Denmark, with offices all over the world. Now, when it comes to Asia specifically, again, Web Structure is headquartered in Singapore with about 100 staff working on high-rise projects. And the rest of in the rest of the region, through Rambo, we have several offices and locations employing over 1,700 experts. Now, within Rambo company, there are a few clusters where high-rise design is being carried out, and Singapore is the leading cluster of high-rise designers. So that's where we hope we can give sharing some expertise today. Now, we have worked on several tall buildings. Here are just two selected examples, from mid-rise to mega tall buildings, anywhere from Europe to Asia and beyond. And this is just a simple collage of some of the picture of the project that we worked on with Web Structures with our well over 700 projects worldwide. Now let's get to some structure, steel structure in Taiwan, which we wanted to talk to you today about because we had the opportunity to work in some projects in this country. Now, if you're aware of Taiwan, it's located along the Pacific earthquake belt, which means that it's subject to very high seismic event. And you can see here by the dots the representation of the seismic event over the past 100 over years. And Taiwan is right in the middle of that area, which is one of the most severe in the world. Now, the country itself is divided in 4 seismic regions. The most severe of which is on the east coast, whereas the city of Taipei itself has its own microzonation, and that is due to some different length of the period of seismic event within the Taipei Basin. So it comes with different zonation. But not only do we have to deal with seismic events in Taiwan, we also have very high wind forces. As you're aware of, Taiwan is subject to typhoon season every year, and the wind forces, the wind speed in Taipei, it's about 42.5 meter per second, but in other area of the country, it reaches up to 55 or 60 meter per second. So that's really high. Now, in this image here, I wanted to show you an example of a project that we're working on, that we've worked on. This is a computational fluid dynamic analysis that we've done for the project. And you can see here the wind flow that we obviously calculated through our softwares and the distribution of the wind pressure. Now, it's very interesting to see, because of a very high wind speed, when we look at the various phases of the building, you can see that the wind pressure goes as high as 4.5 kilonewton per square meter. and that is just for a 30-story building, so it's relatively high. So when we consider both seismic and wind forces of this magnitude, the design of tall buildings in Taiwan becomes a very interesting, very challenging engineering for engineers. In Taipei, obviously, there's one of the tallest building in the world, which is the Taipei 101, but there's several other tall buildings. The interesting fact about those buildings is that most of them, according to the CTBUH, are steel structure or composite structure. So that shows how this material, it's obviously performing well and providing a very efficient structural system against high lateral loading such as seismic and wind. So to design these tall buildings, obviously in steel, we start with a frame, and the frame is obviously formed by columns and beams. When it comes to columns, most of our projects actually did not use just simple steel column, but we always use the composite form of for the structure, which is a concrete filled steel tubular columns, which basically take advantage of the high tensile strength of the steel, but also the high compression of the concrete, and the concrete also prevents the steel column from buckle. So it's a very good, effective solution. You can see from this example of our project, we can study customized column shape and sections, varying the plate thickness, the steel grade, the concrete grade, so to find the best optimal solution. So it's a very efficient column system. When it comes to the beams to form the frame of steel buildings, we typically don't use standard section, and that is because if they're part of the lateral load resisting frame, the lateral load resisting system, these beams tend to be subject to very high demand at very high forces. So in order to, so standard section would not be able. So we typically use built up steel girders, whether they're single plate or double plate girders. Obviously, very particular detail needs to be developed for the connection with the column, where we have a weak beam, strong column kind of connection. Now, the interesting thing about detailing or customizing and building up those girder is that the engineer, the designer, is free to refine and optimize the thickness of the webs and of the flanges, as well as the depth of the beam. So in this graph, you can see for one of our projects, we studied a variation of the depth of the beam and how that would impact the overall performance of the building and the steel quantity. So it's very useful to actually optimize the quantity of steel and improve the efficiency of the structure. Now, to improve the efficiency of the structure even further, we often introduced bracing into our structures. Typically, concentric brace frame is the most commonly widely used bracing system. However, what I tend to do is to concentrate and increase the axial force into the column and have high stress test concentration, which is not ideal. And very often they're subject to buckling. So for high seismic region, they're not necessarily the best solution. So what we tend to prefer are eccentric brace frame, which are called eccentric because they're eccentrically connected to the columns or the beams. And the advantage of these over the concentric is that they have a greater capacity to dissipate energy and to deformate, which is what we want under seismic design. They come in various arrangements, as you can see in this picture. But the advantage of this system is that basically under high horizontal loading, whether it's seismic or wind, they help to dissipate the energy. They do that through the yielding link, which is the eccentric connection of the bracing, which you can see in this image here. When subject to horizontal forces, most of the deformation is happening within the link. So that link would deform plastically, but the rest of the structure remains under overall elastic behavior, which is great for seismic design. So they have a very high ductility behavior overall. And the link works whether it's at the center, like in this chevron bracing arrangement, or at the side, like in the diagonal arrangement. An alternative, I mean, we use this bracing a lot, and you can see a couple of examples in these two projects that we worked on. You know, the arrangement of the bracing is relatively flexible and can work even on a multi-story arrangement, creating some very architecturally friendly and expressible buildings. Now, an alternative to the eccentric brace frame is actually the backing restraint bracing, or BRB, which they are located concentrically, as you can see in those images here in some of the projects. But the advantage is that the core of the bracing is actually restrained by an external steel casing and mortar, so to prevent the bracing itself to buckle. So it becomes a very effective structural, it becomes a very effective system as well, and it performs a lot better than typical concentric bracing. So it is widely used also in Taiwan, and it helps in maximizing the performance of the structure. And this is an example in one of our buildings where you can see a multi-story BRB bracing being adopted. Now, when we do design our building, we studied several options. So we do several option studies to study different arrangement of the bracing, to whether it's concentric, eccentric, multi-story, single-story, and that helps us to find the best performing system. So you can see here in a normalized, in this graph where we normalize the interstory drift in the two directions, it helps us identify which system performs better. So at the end of the day, we can select the structure that is the most efficient for our client, and the most efficient structural system, which is also environmentally friendly. To further improve the the structure and the efficiency of the structure, we also very often in Taiwan consider addition of dampers. Now you can see in this image in some very known buildings worldwide the percentage of damping ratio which was added to the building itself, and that is because dampers obviously improve the performance of a building significantly. So if this is the simplification of a structure, by adding dampers, we actually add negligible stiffness, almost negligible stiffness, but we significantly improve the damping coefficient. So the result is a structure that has a much higher damping ratio, like this example shows. Now, increasing the damping ratio is useful because it allows us to, it allows the structure to perform better under horizontal loading. So, for example, when you look at this graph, you can see how the addition of dampers obviously decreases the response amplitude of building, which is what we're looking for. This graph shows how increasing the height of a building, like the higher is a building, the taller is a building, the lower is the inherent damping of the structural system. So this is a suggestion to us that actually the taller we go, the more damping we need to add, because the inherent structural damping is actually low. Adding dampers also help us to reduce the acceleration of a building, which is very relevant when we design for tall buildings. And reducing the acceleration basically helps us in increasing the human comfort, but also maintaining a very efficient structure. Now, there are several examples of dampers. One of these are obviously tune mass damper, like in this case, but we rarely use those because they tend to be very heavy, occupy a lot of space, and they're tuned to one frequency only. So we prefer typically viscous dampers, whether they come in this shape, which are wall viscous dampers, or whether they are the classic well-known piston dampers, which can be arranged in several ways, horizontally or diagonally. Now, the adoption of these viscous damper, which we can see here in some of our projects, actually help reduce the lateral load demand, improve the displacement of the building, the acceleration, and ultimately results in structures that are more cost-effective, like significantly cost-effective. So that was a brief flight through our projects in Taiwan, and now my colleague Wang Yu will talk to you about our project in Bangladesh. Wang Yu, you're muted.
Sorry. Hey, thanks, Giovanni. Yeah. Just a bit introduction myself. I'm Wang Yu, working in Singapore office of web structures. Yeah. So I have 10 minutes and just quickly brief through those one project, which is we are working in Bangladesh, Dhaka. This is for Bra University. So this is the project overview. Bra University actually requires one campus with multi-story high buildings that contain all the activities and all the classroom, laboratory together. Yeah. So this is due to the requirement of this very higher demand in terms of the space, especially and the ground floor. They need to have the large, space, like looking for the 27 or even more in terms of span. So the steel material of the steel will give the best so-called the solution, and I will see the design approach for this project. So we have designed this the so-called the concrete field columns, steel column, all the way from the basement. They have basement, 3 basement, to the level 4 and level 5, and with the V shape of the so-called the structure forms and the transfer and the level 5, and all the way to the roof. So this is the so-called the overall project introductions. Next slide. As we all know, that in Dhaka, Bangladesh, actually we need to design a higher wind speed. This is talking about even up to the 5.7 meters per second. This is, I think, talking about the 3-second gas. Yeah, but this equivalent to the 43.8 meters per second hourly. It's quite high in terms of the design for wind actions. And also we need to take care about the seismic. For this project, we are looking for both locally as well as based on the ASCE. Yeah, to talking about the short periods of acceleration and the 1 second period of accelerations for design. Next. And this is basically the inter-story drift we are checking, just roughly checking out the performance of the buildings. Thanks. Thanks. It's very interesting for the basement because we have 3 basements, and this is like the first deep basement in Dhaka for the construction. So we introduced diamond wall. Actually, it's our first diamond wall construction in Dhaka. Together with the build 4, you can see here is this temporary RC shrouding system in order to do the basement excavation from the bottom up. So they have basically there's 3 levels of the temporary RC shrouding structures. Next. So as long as we reach to the basement immediately, because of the beauty of this steel structure, we can erect the steel structure from the base, from the so-called B3 parquet and base slab, and all the way to the level 4. Yeah. Underneath the so-called V shape of the structures. And this this column is made by the customized steel tube, 900 in diameter, with the high concrete strength in field. To solve the fire issue, so-called the fire, to provide the fire protection, we also introduced the 75 thick of the concrete in case. So this is very, very good and successfully done by the contractor on site, yeah, with the supervision by this office. Next. You can see some samples of this analysis, modeling, as well as real site conditions when the steel supplier and a fabricator erect this on site. So this is quite large, good 27 meter span with starting of this V-shape transfer columns. We run the final so-called final element analysis with stress check for both transition condition and as well as permanent conditions. Next. More steel erect on site. you can see there's a lot of the so-called the columns with the girders, as well as the scaffold on top. On top of this girder, there will have a secondary beam, so-called the secondary joist, composite beam design, with the composite floor above. But all the steel girders were designed for the seismic because it's the earthquake resistance. So design considered as a primary lateral force resistance system. Next. This is one of the steel giant girders. I mean, transport the columns above, supporting another 11-story above. So this is a very huge size in terms of the column. We're looking for this almost like 1.5 or 1.2 meter in size, with all the concrete infilled. Then this is to create the space below for the event hall underneath. Next. And this is the construction and this design and construction for the V-ship, because this V-ship actually transport and extended to 2 floors from the level 3, level 4 to level 5. So you can say the analysis and the design for all the external and internal stiffness when doing the connections, as well as when the contractor is doing the site installation. Next. This is very interesting. On top of the roof, we're also doing this. The one side is a spire staircase, it's a floating staircase. Mainly is purely made by the steel plate, and around the steel column flying from the level below to the level above. We also have the steel structures which were designed hanging from the roof to create the running track for university. So the faculty, staff, and the students can use this as like the sports activities. So the tower check in terms of vibration, and under the seismic, so-called under the so-called steel structures behaviors, have the design for that. Next. And this is the current status. It almost reached to the roof. We're going to be erect the roof, so-called the steel frame above, provide the PV panel on top for the sustainable features. So this, I think, more or less is close for this. Finish my introduction for the Bangladesh Prague University project. Next. We have some selected projects in other countries would like to share with us. This is a completed project in Singapore for the media, so-called MediaCorp Singapore new campus, and this involved huge cantilever steel structures, more than 20 to 25 meters, and also huge so-called the transport girders and the trusses to support the studio inside. And so all the activities, all the rooms, all the studios is always in the one campus. Next. And this is another project we have successfully done in Malaysia, KL. So this is the Asia School of Business. We've done a lot of the so-called beautiful steel roof and over the atrium. Next. Now this tall building in Singapore is is under the designing stage now, near the Orchard, called the Orchard Gate. Yeah. So this is what we'll have to build with by the steel structures. Next. And this is probably talk to some so-called the somewhere in certain occasions. This is the Kokata Daya steel structures over the two towers. The spanning is 60 to 80 meter apart. Yeah, with the bearing and with on top of the roof. Yeah. Next. All right, this is the end of my presentations. Yeah, thanks.
Thank you so much, Mr. Vigano and Mr. Huangyu, for such a wonderful presentation. Mr. Subrat Panda, requesting you to please share the screen. Over to you, sir.
I hope the presentation is visible. Yeah.
Yes, sir, it's visible.
Yeah, so good evening to all of you, and I thank you for joining this session, and I thank the panelists also who are there in this. So I'll just run through a quick presentation on what we do at JSPL. So we are basically based out of Raigad and Angul in Odisha, and structurals that we manufacture in Raigad. So we have two plants, one at Angul, one at Raigad. Angul, we do about 5.5 million tons in a year, and in Raigad we do about 3 million tons in a year. We have a standalone plant also at Patratu, wherein we do the rebars and the wire rods, but there the steel is supplied from either Raigad or Angul. So effectively 3 plants we have in the India manufacturing locations. Plus we have one more small plant at rebars in Nalwa, and structural fabrication divisions across 3 locations. So we are into both flat and long products, but primarily we are a long product company. So I'll just get into the details. So this is what we manufacture: TMT wire rods, plates, rails, structures, seat piles, coils, hot rolled coils, and rounds and prefabricated steel. So these are the major product lines that we are into. In structurals, we manufacture angles and channels, beams, columns, sheet piles, and crane rails. Angles we do from 75 mm to 250 mm. Channels we do from 100 mm to 400 mm. Beams we do from 150 mm to 900 mm. Columns again we do from 150 mm to 356 mm. Sheet piles we manufacture one size, that is 400 into 170. And crane rails we do in 80, 100, and 120, all 3 sizes. We also have a fabrication plant at 3 plants we have. One at Punjipatra, which is the largest. It has an installed capacity of 10,000 tons. We have one at Angul, which is again 10,000 tons, and at Raigad we can do 2,000 tons. So overall, we have a fabricated structural facility that is either from roll sections or from plates, wherein we can fabricate a final structure. That is about 22,000 tons in a month that we have. The fabricated, these are the lines available at the fabricated facility. So all of these are available at the plants that we have. And they also help with detailed modeling and fabrication drawing, site supervision and erection guidance, design and engineering, fabrication in the state-of-the-art manufacturing facility. This is for the. Now, when it comes to the roll sections that we have, the roll sections that we manufacture are all parallel flange beams. And we were the pioneer in the parallel flange beams in the country. We started way back in 2009 with the parallel flange beams. And parallel flange beams we manufacture from 180 mm to 900 mm. And in that, this is what is the size range that in NPB, what is the narrow parallel flange beam, we do from 180 to 600 mm. In the wide parallel flange beams, we do 160 to 900 mm. Of course, in some of the sizes. In the universal beam, we do from UB 150 to UB 610. And in universal columns, we do from UC 152 to UC 356 into 406. And we manufacture in all the grades, starting from E250 to E450. And also in the grades of ASTM 836, 572, EN, and corrosion resistant grades. So this is what was the earlier available in India. This is what is the typical tapered beam, wherein it was generally available from 200 to 600 mm with a taper. And this is what we manufacture, a parallel flange beam, where both the flanges are totally parallel to each other. and we manufacture up to 900 mm. The advantages of a parallel flange beam is all well known to you, and just one of the major failures which happens in a tapered beam is due to the tapering of the section which is there, and then because of that we need to use a tapered washer, and that is where the maximum failure happens when it happens in a tapered beam. In a parallel flange beam, the connection length is much lower. There is no such problem of using a tapered washer, and so the bolting is much more secure, and the connection length is lower than what is required for a tapered section. And apart from the sections that we have already making, these are the sections that we are currently developing, and will be ready in a period of another 3 to 4 months in all of these sizes. So we are making sheet piles in 600 into 430 mm, what is typically called as PU18 and PU18 plus. Then we are, our current sheet pile, we are reducing the weight of the sheet pile, so reducing the weight of the web. And currently it is at 15.5, we are developing 10 mm and 12 mm in this. Then in UB, we are introducing all these sections. That is UB 406, UB 610, IP 750, UB 762, and UB 838. And also UB 450, UB 500 into 180, and UB 533 into 165. These three sections have come typically from the building segment, the commercial building segment, wherein they said that these sizes would help in designing the buildings much more efficiently. And this is what we have come up with these sizes. So structural steel as it is available across the world in a number of instance up to 1100 MPa, but currently we are manufacturing in India, most of the designing is still happening in 250 MPa. And we have a capacity of supplying everything in 350, 410 or 450 MPa. And that is where the, if you start designing in that, then you have a high strength to weight ratio, a lighter weight, and a cost effective construction. So this is what a typical, what happens if you move from E250 to E450. Is that E250, say E350, your strength, typically it is that your yield strength increases by 10%, then your steel consumption goes down by 5%. But since there is an additional alloy cost which is added to increase the yield strength, so the cost saving is about 1/3 of 2/3 of that. So that is why the strength will increase by 20%, but the cost saving will be about 14%. So that is what is depicted in this, that if you move from E250 to E450, your overall saving in steel in terms of cost will be about 30%, whereas your overall saving in terms of weight should be about 80% on a thumb rule basis. So I'll just cover the structures that we have done in E410 and E450 grade. In flyovers, we have done ITD cementation in Kolkata Metro, and we have also done it for the Mumbai Metro, the underground sections. In E410, we have done it for MG Setu in the Mahatma Gandhi Setu in Patna, and also way bridges we are doing. E450 steel we have been using for this commercial buildings in the Phoenix Group of Hyderabad. We have done it for the Dhirubhai Ambani Convention Center, and also for this Central Vista project. There were 2 office buildings which came up. So there the entire steel structure was in E450, and that was supplied by us. In E450, we have also done this commercial buildings in Noida. And sheet piles, E410 and E450, we have been doing in a lot of years. So these are some of the typical projects that we have completed. So I'll just run you through this. Sheet piles, this is what a product that we supply, and we are the only manufacturers in the country today of hot roll sheet piles. So this is how it is. It looks like it is basically 2 U-shaped sheet piles which conjoin together at this locking, and they give a. So these are the typical pictures. If you go at the Mumbai Coastal Road project, so across Nariman Point, if you look out into the sea, then you will find these sheet piles have been used, and these have been used. And in this current storm which came in Mumbai, they were very effective protection for the site which was outside behind this. So that's all for the presentation. Thank you so much.
Thank you so much, sir, for the wonderful presentation. Over to you, Jay, sir. You can share the screen.
Thank you. Are you able to see my screen?
Yes, sir.
Perfect. Firstly, thank you so much, SCS and JSPL, for organizing this. It's definitely an interesting topic and quite relevant. I quite enjoyed your take, Wang, and I think it's interesting from a technical perspective. I have chosen to do a more macro sort of answer to this. The last few months, everybody's really been talking about steel with me, and mainly they're concerned about, there's a steel prices have been going up, and we've been asked quite often with regards to what is this impact on real estate, and obviously specifically what impact that has in terms of the steel constructed buildings. This is not, of course, a purely Indian phenomena. Even internationally, if you look at the futures, there was a pretty specific spike in May, but this is across the year. But even across 5 years, when you look at it, the steel prices have been going up. Now, the most common question that is asked is, why are we looking at steel necessarily? And it is obviously more expensive. If one were to look at a cost to cost basis, it is obviously more expensive than typical RCC construction for most projects. So what I felt might be helpful to talk about here is that where did it make sense to look at steel, and actually take through some case studies of projects where it made sense to do it. So specific to high-rise and mid-rise, I feel that it's often the question that becomes more important than the answer. So I feel that the question of why should I do steel is not necessarily the right question. I feel it is more, there are a set of circumstances that guide every project. And typically, some circumstances lead to a particular construction methodology. So I find that it's better to understand the project holistically, and for technical reasons, for commercial reasons, for other reasons completely. Sometimes the answer of construction technology comes from those things rather than just a question early on of why not or why, for example. So to give you a little bit, we're Access Architects. We've been working in Mumbai. We completed 40 years last year. We've been doing a lot of mid-rise and high-rise projects across India and now the world. And to give you just a snapshot, these are some of the projects that we've completed on the skyline of Mumbai, looking at it from sort of Chowpatty, Marine Drive, etc. And we, of course, come with a large experience of high-rise and mid-rise buildings in the first place. And what we found as we went through these exercises is that in some cases, it made a lot of sense to start looking at different construction methodologies. And that included, of course, steel and composite steel, for example. These are some of the buildings that we've done in composite steel mainly. This is one of the case studies that might be interesting. This is a project we completed at Navi Mumbai, which is about 2 million square feet, a commercial building and the married executive apartments. The project was interesting because of two reasons. One, we find that when we start looking at commercial buildings, especially when we talk about A-grade commercial buildings, time becomes extremely important. So a project that otherwise might have taken 4 years, 5 years, if you're able to complete that in 2 years, 3 years, that makes a big difference because your leasable rent, etc., starts earlier. Second, more and more, everybody's looking for flexibility. So if one is looking for flexibility, our spans need to start increasing. This is, of course, just a very, very basic sort of table. This is not necessarily always true across board, but this is sort of a guide to look at where does it make sense to do what. So we found that as we start going towards larger spans, it made a lot of sense for us to start evaluating composite steel. in this case specifically, because there was already some work done with regards to regular RCC, we actually had spent some time on doing multiple different options with regards to different construction methodologies. And one thing that is not necessarily looked at is the area that the structure takes within the same building framework. So if you're creating, for example, a floor plate of 50,000 square feet, what is the amount of area that the structural system is taking in one option or the other? Are we able to add more desks if we were to choose one structural system to the other? Those are all decisions that one needs to take architecturally before we start reaching out to the structure and the various contractors, because it is important to take a more macro decision on what makes sense for that particular project. This kind of gives you an idea of the grid distance becomes much larger. With that, your efficiencies in terms of open space in the office, as well as the parking. We got an actual parking efficiency of about 25 square meters of car park. That is without accounting for any stack, mechanical, anything. It's just regular car parking on floor. So what happens when we start talking about it, this gives you an idea of the real world photographs. So it gives you an idea of the flexibility that this affords. If you see the proportion of the columns versus the proportion of the open space, this would become quite difficult to do in traditional construction, even when one were to look at PT, for example. So these are, of course, as we started completing, but you start seeing that there are clear advantages to start looking at this, especially when one looks at grade A office space that is to be put on lease. We feel that there's a very, very good reason to start looking at composite steel specifically, even with the kind of prices we're talking about. And it's very hard, the Indian mentality, because I'm supposed to talk about the Indian perspective. The Indian mentality is, you would usually get a question like, how expensive is it? What's the cost difference in rupees? So, obviously, unless one designs the building, has an understanding of what the slenderness ratio is, what are the other concerns attached to it, it becomes very difficult to, put a number of it straight off the bat. But we found that from a design perspective, as well as from a commercial perspective, it did make a lot of sense in certain cases. This is actually a very different, typically what one finds is that as the building starts getting slender, the cost differential starts increasing. He mentioned a little bit about moment connections, etc. So what happens is that this was a building, is about a 201 meter tall building on Altamont Road. We worked along with Hadi Tehrani on this project. And, I would say, championed the cause of composite steel on this project because we felt it's very important for two reasons. One, the project being on Altamont Road on a rather tight site, our entire site is about 2,500 square meters. And let's just say it's not the easiest, Altamont Road is not the easiest place to do construction. So where otherwise you would expect a slab cycle of anywhere from 7 to 15 days, a typical slab cycle on Altamont Road for a typical building would possibly be about 1.5 times to 2 times that, just because of road movement and a lot of other non-technical things. So as we started going tall, one started seeing an opportunity of changing what the dynamics are because of the speed. Second, what happens is that also when you're talking of some of the most expensive real estate in India, you're also talking about the value of that carpet area that you're reducing. So again, to sort of put a different spin on this, it's not necessarily only about, from a construction cost to construction cost perspective, what is that saving? There are actually a lot of factors. So here, that extra carpet area on a building like this would have, the construction cost is honestly inconsequential. So that little bit of a difference in construction costs does not really make that much of a difference on a project like this. And what we found is that it's about recognizing or asking the right questions to be able to figure out where does some technology make sense and where doesn't it make sense. So this gives you an idea of what our floor plan looked like, and it was a strong concrete core and periphery steel columns which were encased in concrete. There is also typically a question that is asked with regards to corrosion, and all of those things are, you know, your building design is necessarily set up based on that. So something like, the advantages of encasing a steel column in concrete, I think there are multiple advantages to doing something like that. Also because, when you're doing a residential building, you don't necessarily want to see open steel columns as part of the design. So what we find here is that more and more as we've spent time on this, it's always about asking what the right questions are to be able to hopefully find the right answer. This is another project which has a very different dynamic. Here, the project at the back is the project that we designed, and the same client actually had the project where the blue and the red is marked. And this was a different dynamic because redevelopments have become quite tricky in Mumbai recently, mainly because there have been instances where developers have unfortunately not been able to give back housing to the displaced residents for decades in some cases. So as the number of residents or tenants one is talking about increases, it becomes more and more difficult for someone to come in and redevelop. At the same time, this is a win-win on all sides because a lot of these buildings are dilapidated. So the buildings don't actually stand for long, but it is about trusting somebody to be able to move out of your house, hoping that you're able to come back in the 3 years or 4 years that you're promised. This was actually an answer to that question. So here, the buildings that are in blue were where everybody was staying. The building in red was actually a community hall, which didn't have anyone staying. It was more of a congregation space. What we chose to do here was actually keep all the buildings in place, just demolish the community hall. The part in yellow is where the current residents would stay. The one that's in pink is where the new building would come up, where there would be a for sale component. And we designed the entire building from the thought process that one wouldn't need to evacuate any of the residents to any outside accommodation outside the site. They would be able to stay on site. Their new building would be ready in front of their eyes, and they would be able to go and stay there. And then we demolish the buildings around. Now, this in this presentation, I'm not really talking about the capital A architecture. I'm more talking about strategy, because often the decision to take one technology to another is actually much wider than only what an architect sees through that narrow lens. An architect must understand the broader context before being able to suggest one or the other. Of course, you would do this with structural consultants, etc. But this allowed the 600 odd residents to sign on quite quickly because the risk factor was much lesser. So the idea here is to understand from a design perspective as well as from a business perspective what makes sense holistically. There are two other things that is very important. One is the value of having vendors, consultants, and PMCs who understand this technology. And that can't be something that we dismiss because it is a different way of doing things. From a licensing perspective to someone coming in to put up a wall, there are a lot of things that need to change as we move towards this technology. And we found that sensitivity towards that becomes more important because there is a change that comes from before to after. This is an interesting project where it's only a 7-story building at near Dadar Parsi colony, which is a very quaint old neighborhood. And because there was a height restriction and because of open spaces, we actually required a 4-meter cantilever to be able to support the building. but we had no space to have a typical transfer floor, which is what you would usually want to do. So here, because of speed, because, again, there were people that were displaced because of this, as well as the fact that structurally one needed to, do this sort of a cantilever, it made sense to start looking at steel. This project, by the way, is completed in pure steel. We didn't have a composite construction as part of it. This is a project that we've currently broken ground on. This is again similar. You're talking about 150 plus tenants that are only on the ground floor. Ground floor retail tends to have a huge rental component attached to it. And again, this being in South Mumbai, the smaller columns help in terms of flexibility as well as better utilization. Here, interestingly, our tenants' residential building also is done in composite steel. So the intent is we have a 70-meter building and a 120-meter building with a podium and retail on top, on the bottom, all of it done in composite steel. And what is interesting, I requested the developer, Piyush Jain of Earth Spaces, to share, some numbers behind it, because again, as architects, we typically are on one side of the table, mainly looking at plans, etc. But this is often the reason why one decides X versus Y. And he actually had spent time looking at just numbers, between business case A and business case B. Why did it make sense to do this versus that? And what we've realized as architects is that we have to understand this side of things a little bit to be able to best advise our clients. Here, of course, when we start looking at the reduction of time, there were a lot of things that start reducing along with it, which are fixed costs that happened on a month-to-month basis. So I truly believe that we must look at design as problem solving at the most basic level. And what architects typically love doing, which is showcase beautiful lobbies and brilliant elevations, etc., is of course extremely important. But this sort of decision making happens because of more strategic reasons. There is absolutely no doubt that the value of technology, if one chooses to do this, is huge, because the chances of changing things on site becomes very little. Having clashes on site becomes very difficult. So we've been using clash detection, using virtual reality pretty successfully on projects like this. And it's important to go back to what we started at, which is, in the old days, it was about saying, if someone would ask us, what is the cost difference between X versus Y? And, people would say, oh, it would be so much. But today, it's not about answering that question today. It's about asking enough questions to be able to recognize the right answer to all of those questions together. And that is my 2 cents worth. Thank you so much for the opportunity.
Thank you, Jay. Very interesting presentation. And I'm glad that you have touched upon other side of the story also, more from developer perspective. And in fact, we would like to hear from Huang also. What is the mindset, maybe once we come to the question answer session, I would love to know in Southeast Asia, why there people typically go for a steel structure. What is the mindset there? So coming to the next presenter that we have with us, Mr. Anil Agarwal, he is going to take us through some technical details of building mid-rises and high-rises, very specific to seismic design. Anil, over to you, please.
Thank you, Avneet. Yeah, can you see my screen already?
Yes, Anil.
Yes, sir.
Yeah, great. Yeah, good evening, everyone. Sorry to hold you up. I know it's already the end of the workday and the end of the weekend, like weekend is coming here. Anyway, I'll try to keep it simple. I'll not show any equations. I know professors like to show equations. I try to avoid that. I hope you guys, and Of course, I was given 20 minutes. 20 minutes is too little to actually cover this topic in enough detail. But I think for a Friday evening, that is enough detail for you. So I think we can discuss more if you have questions in the question answer session. You have been given, the audience has been given some brief introduction to most of the seismic design systems that are typically used. Some nice buildings were shown from Taiwan and Bangladesh, where they had used different seismic resistance systems. This discussion, basically in this discussion, I'm just going to give you an overview of state of the practice. So I'm not going to talk about the state of the art. I'm not going to involve any fancy systems that are still in the development stage, or some proprietary items are only available. I'm going to talk about things which any architect or any designer can implement in their projects. We'll try to give primarily an overview. I'm Anil Agrawal. I am a faculty at IIT Hyderabad. So as you all know, probably, what do earthquakes do to structures? So earthquakes are nothing but shaking of the earth, right? Shaking of the ground. And since the structures, these are not rigid systems, these are flexible systems, and therefore they respond to earthquakes, right? And they respond elastically, and sometimes plastically, and sometimes otherwise also, right? So if we were living in Tom and Jerry's world, our structures would deform this way and they would not collapse. But in real world, sometimes structures behave this way, right? So what happens to structures when there is an earthquake, when earthquake hits? Earthquake, of course, shakes the structure's foundation, but then what does the structure do? So here I have a very small kind of a demo. It is kind of a toy demo, but it should bring home the point very vividly. So what you see here is a spring mass system. There is a spring which is hanging from this pulley, and there is a mass attached to it. This entire system is sitting in a viscous medium. Okay, so that is not relevant for this discussion. What you see here is that this string is attached to a motor which is exciting, which is giving an excitation to this spring mass system, and as a result, this string will be oscillating, and that oscillation will cause the oscillation of the mass. Let's watch the video. Now, in this flag here, you can see this red flag that represents the excitation amplitude, and the movement of the red body here that represents the excitation of or the movement of the system or the structure. And you can see that the excitation amplitude is much smaller than the excitation of the structure, right? And the reason for that, obviously, you are all familiar with the concept of resonance, so at least you are familiar with some level of dynamics. The reason, of course, for that is the frequency interference. So there is a frequency, natural frequency of the structural system, that is that spring mass system, and then there is an excitation frequency. And if the two frequencies have any kind of closeness, they are close to each other, then this amplification happens, right? Structures also are kind of spring mass systems. They have elasticity, they have mass, right? So they are spring mass systems, and they have their own natural frequencies. We can represent the same thing in terms of time period, right? And there are various ways to estimate the time period of any structure. There are empirical formulae available. So this formula I have taken from IS 1893. I hope all of you are aware of IS 1893 part 1. So based on the story building height and the horizontal dimension, you can measure the time period. Also, there are some rule of thumbs. Also, you can do modal analysis or some other fancy analysis to calculate the time periods, fundamental time period and subsequent time periods for the structure. Now, if we know the time period of a structure and we know what kind of earthquake motion we are expecting, can we calculate the forces on the structure? Yes. And the approach for that would be, here I am plotting the acceleration time history of the ground. Okay, so this is for a particular earthquake. You can measure what is the maximum acceleration that took place during this earthquake. So let's say we pick one peak that is the highest in positive and negative side. Let's say it turns out to be 0.35 g. That is the maximum acceleration. Then we can do some kind of mathematics to derive the response of a system which has a particular natural frequency. And if its natural frequency turns out to be somewhere in this range, let's say, then the system gives me a response of, for this same earthquake, the system gives me a response of almost 0.9 or 0.85 g, right? So even though the earthquake motion was only 0.35 g, I got a response of 0.85 g, right? So it's a amplification of almost 2 to 3 times, right? So therefore, the structure would require to resist a force that is almost 2 to 3 times the ground acceleration, maximum ground acceleration. The same response spectrum that you just saw has been approximated as a design spectrum in the Indian code. Similar design spectrum are available in all the international codes. So you look at this design spectrum, you have your structure, you pick your structure, you pick the time period, and from here you can get the amplitude of acceleration that you are expecting on the structure, right? So let's take one case. Let's say we take a case of a building which is in zone 5, that is very, very earthquake prone areas. So some areas in Gujarat, Assam, and so on, and Kashmir. So some of those areas come under this category, zone 5. And let's say the structure is such that its natural frequency lies in this time period band. So therefore the amplification will be about 2.5. And if we just do a simple calculation based on this, what we can find is that the Indian code would say that you can expect, if the system is a perfectly linear system, you can expect the lateral forces on the structure to be almost 67%, 67.5%. It's self-weight, it's total weight or seismic weight, you can say. So lateral forces being so high, almost 67% of its own weight, these are huge, humongous forces. Most of the structural systems that we design these days cannot resist that kind of a lateral force, right? If we are going to design every structure for these forces, they are going to turn into bunkers. We can't really, we can't have any of the structures that you saw pictures of just a moment ago, right? So obviously there is something we have to do. And also there is a lot of uncertainty in predicting the earthquake motion. So even this much of force may also not guarantee an elastic performance for the entire structure. So a design philosophy is adopted. This design philosophy is basically based on the capacity of the structure, not really based on the demand of the earthquake. It depends on the capacity of the structure. So what do we say? We accept the fact that we can never design a structure which will remain elastic, or we don't want to design a structure which would remain elastic during the design earthquake, right? So what we say is that, okay, let's accept the fact that some components of the structure are going to undergo inelastic deformations. That is, in other words, damage. That is permanent deformations, right? And if we allow that, then what will happen is as soon as one element undergo plastic deformation, it will not resist additional load. So for example, if we were to do the elastic analysis for this system, and this is one component, this is the force versus displacement behavior of a component. Under the elastic analysis, it would have taken this much of load, right? But what we say is that, no, we have designed this component in such a way that after this much of load, Cy, it will undergo yielding and it will carry only, it will go on deforming plastically, but will not take any further load. So by doing that, what we have done is that we have reduced the earthquake force demand from A to C. Okay. So in this philosophy, when we follow this philosophy, what happens is that now we have to split all the components of the structure into two parts. And I'm talking about, when I say structure, I'm talking about only the earthquake resisting system. In steel buildings, often we have separate frames which are meant for earthquake resistance and separate frames which are not meant for earthquake resistance. So whatever discussion I'm doing is only for the parts that are supposed to resist the earthquake. So then we split all those components into two categories. One category is called deformation or ductility controlled elements, right? So these are the elements which we are expecting to fail. Not exactly fail, like they are not going to break, but they are supposed to have ductility and they are going to deform plastically. Okay. And there is another set of elements which are neighboring these elements, which we cannot afford to let them undergo plasticity, because they are very, very critical for the health of the stability of the structure. So columns, in every single case, columns cannot be allowed to undergo plastification, right? So columns remain always in this category, FCE. So they cannot plasticize. Depending on which kind of structural system we are dealing with, if we are dealing with a moment resisting frame, then the beams, rather beam ends, they are supposed to behave as DCE, ductility controlled elements. In a concentric braced frame system, if it is not buckling restrained, that is a separate category. If it is a regular concentric braced frame system, then the braces themselves are supposed to undergo ductility, exhibit ductile performance. They are supposed to plasticize. So they become DCE. In an eccentric braced frame system, as it was discussed in the first presentation, the shear links, right? These can undergo significant plastic deformation, and all the other structural components here will remain elastic. So now we have figured out, okay, so we have found a way to reduce the force demand on the structure, because we are saying some components will plasticize and they will not resist any more force. So how will the earthquake apply more force? Because the components are not willing to resist. So they will keep deforming. Fine. So that gives us some hope. So how do we adopt that into the design? What we say is that this was the design spectrum that we had developed. This was for an elastic system. what we say is that, okay, this R we can figure out from the structural system, and we can say, let's reduce our elastic design spectrum into an inelastic design spectrum by multiplying it by 1 by R. So we multiply this design spectrum with 1 by R, 1 divided by R, we get the inelastic design spectrum. Now we will use this one for our designing. So for calculating the load demands, we will use this design spectrum. But please remember that what we are doing here is that actual elastic systems response was supposed to be A. We have reduced that to B, right? Now, basically we are saying that, okay, our forces have reduced from A to B, but at the same time, when you do the analysis with this revised force demands, your displacements will also be reduced from A, that is theta E, to delta Y, right? But that is not the actual displacement now. The actual displacement would be something called delta U, right? Because now the system is behaving this way. It is not going on that path, right? So now artificially, we have to increase the deformation demands. Force demands have been artificially reduced, but displacement demands have to be artificially increased. And that factor is called CD, C sub D, which takes into account the inelasticity or the additional deformation that you get because of inelasticity or because of ductility. Okay, so we reduce the force demands by R, we increase the displacement demands by CD. There is one more factor that we must be familiar with, which is called overstrength factor. You remember there were two categories of elements. One category of element was DCE, which was supposed to resist, which was supposed to plasticize, and the other category of element was FCE. So for the FCE elements, they are not supposed to plasticize. That means they should have a strength higher than the neighboring DCEs. So if a DCE is going to yield or plasticize, the neighboring FCE should not plasticize because of that. That means the FCEs should be designed with some overstrength, some extra conservatism should be built into those FCEs. And overstrength factor is used for designing those kind of elements. I'm not going to go into too much detail here. Here, I'm just giving you one example. So this is a moment resisting frame. So the beam design would be governed by DCE. So it will be done as per DCE by dividing the earthquake forces by R. However, the columns, for example, or the moment on the columns will be designed as per by increasing the earthquake demand. So earthquake demand, this one is already arrived at by dividing by R. Now we multiply it with gamma 0, a factor, overstrength factor, which increases the earthquake demand for these members. So FCEs will be designed according to that. And there is one more approach. I'm not, again, it will take me on a different path, so I don't want to go on to that one. There are three primarily commonly used three types of lateral load resisting systems which are in use, and they are good for different height of structures. So for example, moment resisting frames are typical rigid frames that we are all familiar with. They are good for structures of up to 8 to 10 story height. Maybe for taller structures than that, they become too flexible because this is not a very rigid system. However, it can perform very well under an earthquake condition if it has sufficient stiffness, that is. So we all know how they resist, how this kind of a frame resists lateral loads. You have a frame, you have two lateral loads acting. This could be representative of earthquake loads, which are inertial loads basically. So basically what happens when this load is applied, this load is resisted through shear forces at the base, individual moment resistance at the base of each of the columns, and also some components of this moment is transferred through the axial forces in these columns. And that's where this rigid connections roles plays. Okay. So if you look at a beam here, the ends of the beam, and look at this column here, ends of the column, they are subjected to largest amount of moment demands. The design philosophy that I had just discussed that wanted to separate the systems which were FCEs and DCEs. DCEs are allowed to undergo inelasticity, and FCEs are supposed to remain elastic. For moment resisting frames, what we say is that columns are the DCEs, columns are the FCEs. They are not supposed to undergo any kind of plasticity, and the beams can plasticize. How do we ensure that? We can ensure that by this philosophy, which is often quoted, which is known as strong column, weak beam design, wherein when the lateral loads are applied to the frame, the beams should yield at any junction. The beams that are coming to that junction should yield before the columns yield. And once the beams have yielded and columns have not yielded yet, then since the beams have reached their capacity, then no matter how much displacement we apply, any additional displacement we apply, the column would not yield. right? So that kind of philosophy ensures the overall stability of the system. If we do not follow this, then you may see that the hinges may form in the columns and can lead to overall instability of the system. There are various types of special moment resisting frame which are prescribed in some of the international codes. AISC 358, which gives you some predefined or pre-qualified connections. So basically, if you go to this document, AISC 358, it will give you a lot of details about how you design each of these types of connections. So there are some 5 types of connections given here. And these connections, it will tell you, okay, what is the minimum moment requirement for this end plate and so on. So if you follow all those instructions, then these connections will qualify the requirements of spatial moment frames. What is a spatial moment resisting frame? It is basically a frame that ensures that the failure is followed or failure takes place through yielding of the beam and the local buckling of the beam or the beam flange or the beam web or the local buckling or the deformations or the bending of the column flange or the rupture kind of failure modes don't take place. So local buckling and rupture have to be avoided, and other types of failure modes are okay. Primarily yielding based failure modes are good. So this is a very interesting design that sometimes intrigues people. This is one of the pre-qualified connections that is available in the AISC document, which is the reduced section connection. So you reduce the cross section of the beam slightly away from the connection. Okay, so you cut a portion of the flanges, right? And as a result, when you design this, when you subject this beam to lateral forces or to moment demands, you would see that the moment demand, even though is higher at the very end than here, the yielding will be concentrated here because the capacity of this cross section is lower than the capacity of this cross section. When they studied this kind of a connection in the lab, they plotted, so they subjected this kind of a connection to a vertical cyclic loading condition, and they plotted force versus displacement for this connection. And what they saw was that they get very nice repetitive curves of this kind, loops of this kind. This is a hysteresis loop. And this kind of a hysteresis loop that has almost a rectangular shape represents a very good hysteresis behavior, which is this kind of a connection or this kind of a member has a very high capacity of dissipating energy, which is the benchmark or which is the hallmark of a good seismic performance. Okay. So we have a very good control of the moment capacity because every single time it ends up being right here, no matter how many cycles we do. And also, even after a 4% deformation, it still maintains almost a rectangular shape. Okay. And because of such a high quality hysteresis behavior, such kind of systems are given a response reduction factor of 8. That is, if you remember the original curve, we had an elastic design spectrum, and then we had an inelastic design spectrum. So inelastic design spectrum can be 1/8 the size of the elastic design spectrum. That is a huge advantage for the designer. However, there are some drawbacks that I've already talked about these systems. There are some extra precautions one needs to take because oftentimes we prefer to weld these flanges of the beam directly to the column. And if we do that, there are a lot of imperfections that we can introduce that can lead to fractures. And there are several precautions mentioned in the document, in the literature. You can go through these, such as you have to make sure that there are no defects, there are no notches available in these welds. Also, any backup bar which might have been used during the welding has to be removed, back gauzed, and another fillet reinforcement has to be provided. So this makes the work a little bit difficult. Other type of structural system, lateral load resisting system, which is commonly used, is called concentrically based frame systems. So here are some pictures of concentrically based systems. You have seen already them, several of them. So here is an example of one. So for example, you have a frame. In order to develop a lateral resistance, if we make all these connections pin, one option is to put these diagonal members. When I apply lateral loads on this frame, these braces are undergoing tension force demand, and these braces are undergoing compression force demand. And when the earthquake direction reverses, then these braces take up tension and these braces take up compression, which is a perfect solution. The challenge is that many a times these braces are so long and slender that they can buckle under compression. When they buckle, then their capacity under compression is very different. It's much smaller than their capacity under tension. Under tension, if we have a rod or a bar, and if we are pulling it in tension, only way it can fail is by yielding. But if it is in compression, once we are pushing it in compression, it can buckle, and that buckling can happen much sooner than its yielding stress level. So here are two possible configurations. I'm just showing a schematic. There is a braced frame system. You have got a column, beam, column, and then you are subjecting it to a lateral force here. So this brace is in tension, this brace is in compression. Under compression, let's say this brace fails first. Now, since this brace has failed under compression, there will be an immediate load drop in this brace, and this brace is still carrying tension. As a result, what will happen is that there will be an unbalanced vertical force on this beam, which may lead to a development of mechanism or yielding of the beam at this location. Similar thing can happen if we use this configuration of braces, wherein if the lateral load is applied, this brace is in compression, it may buckle, leading to an unbalanced force on the column, making this column undergo yielding here. Between these two configurations, this is acceptable because even if a beam yields locally, it is not going to cause a global collapse of the system. But if this column fails locally, if a column develops this hinge or yields, it may lead to a global collapse of the system. So therefore, this kind of a configuration is prohibited for earthquake safety point of view. Okay. So there are some set of configurations I've listed here, which are permitted and these are not permitted. This is as per AIC document, and they are pretty obvious. There is another challenge with braced frame systems, concentrically braced frame systems. Often we use hollow sections for concentrically braced frame. Why? Because we want to increase the buckling resistance. How do we increase the buckling resistance? By making sections hollow, right? So most of the material is placed farther away from the centroid. As a result, the flexural stiffness increases, flexural moment of inertia increases, and as a result, the buckling resistance increases. But such kind of hollow sections also have another weakness. Since they don't have thick flanges like an I section, this can sometimes be, they can easily undergo local buckling. And if there is a possibility of local buckling under, especially local buckling requires large amount of strain development, and that in cyclic conditions can lead to low cycle fatigue, something called low cycle fatigue, which cause a fracture of this element. Okay, so there are several such limitations. And then if you want to design a concentrically braced frame to be special concentrically braced frame, you have to abide by very strict requirements of compactness of the cross section and so on. As I was explaining before, what we do is, let's say we have a brace here, we subject it to a compressive force. So this is how we start the loading. This is compressive force we are applying. As it reaches a particular stress value, it will buckle, right? And as soon as it buckles, the force drops. So this is on the horizontal axis, I'm plotting the deformation. Vertical axis as the force. So the force would immediately drop, and then I reverse the direction of the loading. I take it to tension. In tension, it would yield. It will carry some tension force, and then I reverse the loading again. But next time when it comes to compression, it will not carry even this much of force. Why? Because buckling resistance is much lower now for this section, which has already yielded once. So this time, this section would carry very small force in comparison to the previous cycle. So basically, this kind of a system is not able to maintain its cyclicity, right? And this depends more peculiarity. This particularly depends more on the slenderness of the member. So, for example, the same graph that you saw before, in tension, for example, this is a strut. In tension, it has a high resistance, and cycle after cycle, it can carry large amount of resistance. But in compression, in the first cycle, it may still show some resistance. But subsequent cycles, the compressive resistance keeps reducing. And as a result, you can see this is basically the hysteresis cycle, hysteresis loop of this brace. And you don't see that rectangular, nice, bulky squares or rectangles, right? You can see that this has kind of pinching going on here. And also this area is very limited. This kind of a behavior is not really a very desirable behavior. And you have to take a lot of precautions when you go for this kind of a brace system. The international codes, even for SCBF, which is basically you have to take, in spite of taking all kinds of precautions in terms of compactness and how the gussets are designed and so on, still you can use only 6.0 as response reduction factor. You can compare that with 8.0, which was available for moment resisting frames, because the energy dissipation is not very good in this kind of a system. The third system that we can briefly touch upon is the eccentrically braced frame system. In this kind of a system, basically, again, you have seen this already in the first presentation. You have these kind of diagonal braces, but you leave some space in between. That portion of the beam is supposed to undergo plastic deformation in shear. So that's why this portion is called shear link. And this kind of behaves as a fuse. Like in our electric circuit, we have a fuse, right? So whenever there is a stress demand, there is a large electric demand, the fuse goes off, but that saves the entire structure. And later on, you can replace the fuse. right? So similar kind of treatment is expected from this kind of structure, which can undergo large deformation and can be easily repaired because it is at a particular location. It is concentrated at a particular location. The entire structure is not damaged. So as you already are familiar, this shear link undergoes shear deformation. This kind of a shear deformation also has some risks. What happens is that if you use a shear panel, a panel like this, wherein you have used a metal plate inside, which is suspected or which is assumed to have undergone shear deformation and plasticize, it may not often plasticize. It may often undergo shear buckling. Shear buckling is also a phenomenon that we study as a part of plate girder design, right? So that may happen to this also. And in order to avoid or delay it, we may stiffen it in between. If we are able to do that effectively, we can improve the performance of this kind of a system, which is quite as effective, almost as effective as the moment resisting frame system. However, developing this kind of a shear links can sometimes be quite expensive. So here I'm showing you a comparison of the behavior of this kind of a shear link versus this kind of a shear link. And you can see that the performance improves quite a bit. So you can see this behavior is almost as good as the moment resisting frames. Okay. And the American code allows you to use a factor of 7.0 for response reduction of this kind of a system. It's a very efficient energy dissipator. Is used in several systems. So with this, I would stop my presentation. I think I've not taken a couple of minutes extra. I'll stop sharing now.
Thank you so much, sir, for the presentation. Before I hand over to the proceedings to Mr. Avneet Singh for the panel discussion, he's the moderator for the day, requesting all the attendees to please participate in the poll and post your questions in the Q&A section, which will be taken over for the Q&A session. Thank you. Over to you, sir.
Thank you so much, Carol. And we had a very interesting back-to-back presentation. And I'm glad that we have such a nice expert who shared their knowledge with us today. If I can request all the panelists to switch on their cameras so that we can start the panel discussion. So if we have Mr. V.R. Sharma with us, there are two questions that are being directly addressed to Mr. Sharma or Mr. Subrat Panda, if he can answer those queries. In fact, one important question is on steel pricing and the trends that are going to follow, or why the steel prices are going continuously high, and what will be the trend in next, if we can understand something about the trend, how it is going to be in next few months or few quarters.
I think Sharma Saab is not there, so I'll take that question.
Okay.
As far as the steel prices are concerned, if you see that it is more of a cost-based sort of price increase which has happened. Iron ore, which was selling at, say, if we look from a yearly perspective, last year or even in the beginning of, say, last October, the iron ore prices were about $90 a ton. From that, they have moved up to a range of today around $220 a ton. And primary reason for that has been that probably there has been a bit of a short supply as far as Brazil is concerned. And Brazil being affected by COVID, I think there was a lot of lower availability which was available from Brazil, and also the dam burst which happened in Brazil about 2 years back. That has also had an effect in the overall availability of iron ore. Almost 40 million tons of iron ore went out of the system because of that. And similar environmental concerns have also affected further mining at Brazil. So that is one reason where there is a bit of a short supply as far as the iron ore is concerned. As far as the domestic iron ore is concerned, if you look at it, we were at around 4,000 rupees a ton about 7 months back. And today the iron ore prices is about 14,500 to 15,000 rupees a ton. So, and in the domestic also the same reason happens is that there were certain mines in Odisha which got closed in from 1st of April 2020. And so immediately in April to September of 2020, it was not obvious that because the COVID was playing in a year. So it was not very obvious of the shortage. Then once the demand came back, then that shortage is still continuing. So there also from that about 29 million tons of iron ore on a annual basis has been out of the system. So both these factors, domestically also the iron ore prices have gone up, and internationally also iron ore prices have gone up. The other, and in making steel, say for producing a ton of structural, you require almost 1.9 tons of iron ore. That is, the iron ore is generally 62.5%. So as it is to make steel, you require about 1.6 tons of iron ore. Then from iron ore, from the hot metal to the final product that it comes, there are wastages along the route. So it is almost on a thumb rule basis, you can say that 2 tons of iron ore is required to make 1 ton of steel. And the other cost input has been the coking coal. So the coking coal was at about $100 about a year back, and about 6 months back. Why 6 months? Even about 3 months back, it was at $107, $110. And over the last 12 weeks, it has now come to a level of $170. And coking coal in China today is almost at $220, $230 because they aren't buying Australian coking coal. They are preferring more of the US coking coal and yes. So coking coal prices in China today is at a 10-year high. And based on the way the things are panning out, see the prices generally are affected if China starts exporting quite a lot of material into the world. And of late, the Chinese demand has been very strong. And they have their own concerns, environmental concerns and other concerns, wherein they have now reduced the exports. And in fact, they have there was an export tax rebate which was available. They have removed that from the year. So unless and until, so now the supply and demand is more or less balanced. And that is how the prices are continuing in line with the international prices. Today, if you look at the European prices for HR coil today is at about $1,450. If you look at the US prices of HR coil, it is at about $1,800. Compared to that, domestic prices are almost, Indian prices are almost 20% lower, if you look at it. And today, if we want to export with a better realization than what we want, what we get in our domestic market. But based on the Atmanirbhar Bharat that we have and our commitment to the Indian industry, we are still supplying whatever is required in the Indian industry. And beyond that, whatever is available, that we export.
Interesting. Thank you so much. Thanks for the insight, Mr. Pandit. Huang, coming to you and Giovanni, when you meet the developers or the project owner, what are the key factors that kind of motivate them to go for steel or a composite building? Jay already given an insight on Indian perspective, and he has showed some cost calculation also. So what are the factors that affect whether this building is going to go RCC or a concrete or a composite or a steel building in Southeast Asia?
Okay, maybe I share a little bit experience here for the project we did. I think there's two main concerns, which is I would say the so-called the requirements from the developer when we approach them for a project and to talking about the material and the structure system to be used. One is definitely the time. Time is crucial for most of the development. The second thing to us is also very, very important. It's called the sustainability. Yeah. So the next we're talking about cost and the efficiency of the floor. Just now the one of architects talking about that one. That's so-called the after the second points. But the first 2 points I would say the time and the sustainability.
Very, 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 very valid points. That's great. So coming to another question, what is the basic difference between an RCC cost-wise? What is the basic difference between RCC building or a steel building? Do you have any thumb rule or some percentage, or it depends upon the structure to structure?
For the different country has a little bit different of the so-called the figures, I believe. Okay. So, but if you're talking about something here in South Asia and in Singapore, and we are talking about the steel. If you talk about same so-called the arrangement of the structure, let's say typical like the floor 9 to 12 column grids. in that sense, the cost of steel will be steel structure compared to RC. We're looking for like the 50% to 80% more.
It is expensive. Steel is expensive.
Yeah, steel is expensive. Yeah, currently
Okay.
still in this range. But of course, the things change. Reason because of the pandemic and because of this issue, and we also in Singapore we are facing a lot of the issue in terms of the manpower and the workers, skilled workers, you know, the on site to do the in situ works.
Okay.
So the things will change. I would say even you have a price, but you don't have workers to do the job.
Okay.
So the prefab for the steel and is a choice of the construction. Yeah.
Interesting. Jay, can you give some insight if you have some numbers? You have spoken on life cycle cost, but overall, what is the cost impact?
So in fact, that's one of the things I mentioned in the presentation, that it's too open a question. But I would actually, the number that Mr. Huang said was interesting to me. I wonder if Mr. Panda would like to sort of, considering you would be doing a lot of projects where you are taking on a project to give a cost in composite steel. I wonder if you would have a percentage that is average for India, because at least in my experience, 50 to 80 seems quite high with what we've seen, but maybe that the experience is very specific.
I think the thumb rule that we follow in India is that when you do it with an rebar 400, 500 and E250 structural, then the difference is about 25%. But the moment you move this E250 structural to a E350 structural, which I also covered in my presentation, that there is a 40% saving in steel and accordingly a 16% saving in weight. So it probably moves to a much lesser percentage once you move to a higher strength steel. And the moment you move it to E450, probably we are today able to design commercial buildings at a total uses of about 5.6 kg for the beams and another 2 kg for the rebars. And that is what is required if you are using it with a composite steel structure with E450. So this is what, and I think it works out much cheaper if you are actually doing it in the high strength steel.
Yeah, I think the numbers are, sorry, go ahead.
Yeah, no, I was just about to say that one thing that is worth probably adding to the conversation is that, you know, the premium of steel gets lower for longer span, obviously, right? So when you look at a standard span, of course, the premium is very high, but when you look at longer span, the premium gets a lot lower because you start saving in not only on the structure itself, but even in the foundation because the weight gets lower, etc. So, you know, it's not a structure. I mean, it's not a question that I have one answer, but you know, all these things need to be considered at once.
A lot of other factors are contribute to the cost. Maybe location.
Yeah. Makes sense. I think I would agree. So my presentation was actually about that. It's very hard to. That question is actually not the right question to ask.
Inevitably, that question comes up.
Yeah, we get that question very often. But I was surprised that you got a percentage out of anybody. but I think, I think what Mr. Panda is saying in the ballpark, depending on, you know, a lot of other factors. But yeah, we found it to be lesser than 25 in our experience, or we don't recommend doing it because, you know, what happens is that Indian market, unless you're doing something like a special project or something like that, Indian clients tend to be quite price sensitive. So what we found is there are projects that one shouldn't really be evaluating, or if, you know, one needs it in a certain period of time, then cost is not necessarily your first thing. Then you know, you want to, then whatever it costs, but we need it in that time. So
like what Juan said is, if the labor is not available, you know,
exactly,
it makes more sense. And I think towards Southeast Asia, there is a lot of, you know, they're very cautious about sustainability, which is very important today. with the current scenario? What are...
No, you'd be surprised in even A-grade commercial. It becomes very important to start looking at sustainability. So
yeah,
I think it is not something which is specific, because now we are talking of a more global clientele also for the people who are going to be in these buildings. So it is important. There's no doubt about it. It's just, like I said, it's a more holistic question to answer rather than a specific kitna deti hai sort of thing.
So coming to Anil, Anil, we have a lot of questions for you. And as I was going through the question session, so Arun Kumar wanted to know, in seismic analysis, which method will be advisable for Indian environment?
See, Indian environment, actually, yeah, Mr. Arun Kumar himself had asked another question, whether seismic equivalent static method would be applicable for zone 3, which I answered already by typing it. It is applicable. This question, I'm not 100% sure what he means by Indian environment. In Indian environment, there are all methods available to be used.
Okay. Okay. One question is, which is very specific, came for you, is do Indian manufacturers require some certificate? Is there any restriction on you being importing Indian steel for a project in Southeast Asia? Am I audible, Juan?
This question for me?
Yeah, there is a question. Yeah. Okay.
Yeah, I think yes or no, because in the different countries have the different regulations in terms of the by using steel. It's just, for instance, like in Singapore, the steel import from the overseas, they need to have certified by the independent, so-called the testers, and complying to the Singapore called the BC codes. Yeah. So as long as we can comply with those requirements, then yes, no problem. Yeah, not the issue.
Okay. Mr. Subrat, there is one specific question which I think you will be the right person to answer. In Europe, there are a lot of service center concept is there in Europe. You see a lot of service centers who can cater to, small to mid-sized demand across Europe. That same concept, we don't see much flourished in India. Do you see, when do you see things changing and we get more service centers in India? And can we see, can we see the steel section being ordered online, like we order products from Amazon and Flipkarts? Maybe can we see that trend coming in, wherein they can place order online also?
So service centers, if you look at it, then when it comes to HR coils, I think we have a number of service centers which are all run by private players, and some like Erstwhile SR had an hypermart and that sort of a model, which is available for more of the flat rolled products. As far as rebars is concerned, again, we have service centers who do the cut and bend, and they are located all across the country, and we also do it at our end. As far as structurals are concerned, it's a very correct observation that there are hardly any service centers as such which are available. But we have got distributors who are there all across the country. So they do stock the material and they do keep the material, but they primarily keep in E250. Still, E350 is not a grade which is very prevalent as far as the distributors are concerned. But we, organization, we do have a lot of stocks at our plant. And we can even service anything which is a full trailer load in multiple sections. So we do service that yes. For example, we have refinery clients like EIL, wherein they require almost 7 to 8 sections in one truck and one trailer. And we are able to service those sort of requirements even in E350. But it is a very pertinent observation that we do need to ramp up our distributor sort of arrangement, wherein they provide these facilities of cutting the material and giving it to size or slotting the material on those sort of efforts as far as structures are concerned. As far as buying online is concerned, today you can buy our rebars online. There's absolutely There's a online website which is available wherein you can buy, anybody can buy the rebar. We are yet to start with structures because we are not too much into the lower sections of the structure. We are more of a heavy structural sort of or a medium structural sort of a supplier. So there the requirements for a home builder or is too limited. So we haven't started that, but this is something that we can also explore. We can't hear you.
We cannot hear you.
So your voice is break. We cannot hear you. No, so you're not audible.
Yeah, hi. Am I audible now?
Yes.
Okay, one final question to conclude today's webinar. Fire is one of the key elements when it comes to high rises. So what is your take on, that in terms of the cost that it adds, how it could be, how those costs could be curtailed, and when you go ahead with any steel building, what is the factor that plays in terms of fire resisting a steel building in mid-rise or high-rise?
Jay would be the best people to answer that.
Jay, fire, how often, Juan?
So I think it's absolutely necessary to talk about this because it is a concern, especially with mid-rise and high-rise buildings. So usually when you design, as you're aware, NBC has very specific norms depending on the project. You have anywhere from 2 hours to 4 hours fire rating that's required. And on top of that, your local government body typically keeps that the same or increases that requirement. I think it is necessary. I mentioned a little bit in the presentation where, especially when we do residential, we prefer to even make the columns of composite action because it also gives us fire resistance. It gives us some level of control against corrosion. So it is one of those things where one must talk about it. And there are, of course, enough technologies available to be able to do that, from intumescent paint to vermiculite, and there are some new things also that are on the horizon. So I think it's fire design or fireproof in a building is just as important as the design of the building, but it is not that complicated or difficult. It is a part of the design of the project.
Just to add a few things on the fire design. Actually, this is one of the special topic in terms of fire engineering to the steel structure as well as composite steel structures. Because apparently there's a lot of the researchers and the academics, so-called the projects, they're looking for the fire, so-called the composite, like the concrete infill tube, so-called CFT performance under the fire. So in the local university in Singapore, there's one so-called study which is ongoing for that. And of course, for practice, for practicing engineer, currently we have to comply with the local so-called fire authority. Basically the best way to do is to do the concrete encase for the structure, for the steel sections, yeah. But if it's exposed to the environment, otherwise, yeah, it's right to say that we put normally we put the so-called the cementitious, the spray, so-called the materials to cover the steel surface.
Okay. Anil, any input from you?
Yeah, actually, the question I think was on the cost side of it, and that is a very difficult question to answer again.
Yeah, that is the reason I just tried to.
So like, see, technical solutions are like, there are plenty of them. Yes. All of them are already mentioned here, and there are more. But cost, it depends on the designer. They can be innovative, and as it was correctly mentioned by Juan, a lot of research is going on into developing systems. So, for example, joists, as per the code, whether it is a beam or a joist or even the smallest segment of a beam has to be protected by the same amount of fire protection. A lot of people, some research started in UK, a lot of research is going on, as correctly mentioned, in Singapore, China, even in India, where people are seeing whether joists also require that much of fire protection, because if you can prevent that, they cover so much of area. They require so much of fire protection, just the joists. They are the largest amount of consumers in terms of fire protection material. So if we can avoid fire protecting the joists, can that help? But as correctly mentioned, codes require it, you have to do it to get the occupation of the building that you built. So yeah, so that's the status. Some municipalities, especially in the Europe, they are more willing to experiment. So they accept if you show a research finding and say that these systems don't require this fire protection. I've got this research paper, it says that this works. Then they accept that finding and they let you do it without they let you violate the code. But I don't know any Asian countries which allow or which are that experimental. Or even in America, it is very difficult to violate the code and do something without.
I think that to add to that, I think that as you're saying is like performance fire engineering that's really can help a lot in improving the fire design and minimizing the fire protection. So that's pretty useful. Yeah, in some countries it's accepted, in some other countries it's not accepted yet. But it's, performance-based design is typically a very good direction.
Thank you so much. Thank you, all of you. In fact, we had a very fantastic panel and very interesting presentations today. I'm glad all of you joined us, especially the attendees also. I hope you had a good time. I know few questions are not yet being answered, so I will request you to write those questions back to us. If you have any other question, please write to edit@mxbm.in. We'll try to get your answers. We'll try to get your query solved. Thank you all for joining us today. Fantastic evening we had with you guys, and look forward to see you again.
Thank you.
Bye-bye. Thank you.
Thank you so much, everyone.
Bye. See you.
Thanks. Bye-bye.